Good evening, everyone. I welcome everyone for the Computational Fluid Dynamics Problem Solving Session 8. So we'll start the session by 6:05. Let's wait 2 more minutes. We'll start today's session now. Till now, we have seen about CFD, like various techniques like finite difference approach and finite volume approach. So in today's session, we are going to see about the solution to Navier-Stokes equation. In previous week, we saw the problems concerning the solution of Navier-Stokes equation for the compressible flows. This week's the main focus was about incompressible fluid flow. So let us move on to the questions. So at any point of time, if you have any questions, please feel free to stop and ask, or else any suggestions or any feedback are also welcome. Now we'll move to today's session. So question 1, which of the following statements is or correct about incompressible flows? Uh, First one, so the figure concerning this week's flow is this, figure 8.1, incompressible flow through contraction in a pipe of circular cross section. So the statements given are, most liquid flows are incompressible. Flow of air can be incompressible if the fluid speed is sufficiently high. So this problem is kind of extension to what we studied last week regarding compressible flows. So what is the options? What are all the options given? The first one is either one is only correct, or second statement is alone correct, or both one and two statements are right. In the last case, neither one nor two. So we'll identify which of the statements are correct. Most liquid flows are incompressible. We know the statement to be true because if we are dealing with the liquid, there won't be much compressible or change in density, so we assume them to be incompressible. And the second statement is, flow of air can be incompressible if the flow speed is sufficiently high. In this, we should think first of all how or when we consider the flow to be incompressible. We consider the flow to be incompressible when the velocity is very low. In such cases, there won't be any deviation or much change in the density of the system. So it is that flow of air can be incompressible if the fluid speed is sufficiently high. The statement is false. Only this statement is correct. So the answer to this is option 1. Most liquid flows are incompressible is the correct answer, while the second statement can be modified as, flow of air can be incompressible if the flow speed is sufficiently low. Only in such cases we can say them to be incompressible flow. We'll see that while all flows are compressible, flows are usually treated as being incompressible when the Mach number is smaller than 0.3. What is Mach number? Mach number is the ratio of speed of the flow to the speed of the sound. So we know the speed of sound in that medium and speed of the flow. If the speed of the flow is very low, automatically the Mach number would be smaller. When Mach number is smaller, we consider the flow to be incompressible. What it means is, when the flow is very slow, the molecules of the would be moving at a slower speed, so their chances of it being compressible would be very low. Here the flow or the fluid does not denote, the compressible or incompressible is generally the part of the flow. So Mach number is defined as, if it is m, it is u by c, where u is the local flow velocity and c is the speed of the sound in the medium. If the local flow velocity is high, Mach number will be large, therefore the fluid will be compressible. So in this case, when the fluid speed is very high, the Mach number would be high, so the flow of air would be compressible, not incompressible. It would be incompressible when the fluid speed is very low. Now we'll move on to the question 2. Which of the following is or among the difficulties encountered in the solution of incompressible flows? Coupled equations, nonlinearity of governing equations, determination of pressure. It is 1 and 2, or 2 and 3, or 1 and 3, or 1, 2 and 3. Which of the following is the difficulties encountered in the solution of incompressible flows? So we can see that difficulties encountered in incompressible flows. What is incompressible flows? In incompressible flows, we know the density to be constant. So what we do, we generally have the continuity equation and the momentum conservation equation, right? Momentum conservation. How these two would be linked? It would be density would be appearing in both the terms. If in the continuity equation, if the density is constant, dou rho by dou t term would be become 0, right? In continuity equation, we have the term dou rho by dou t. This would become 0 when it is incompressible flows. So in such cases, we cannot solve the coupled equations. I mean, we need to find a different approach. So the coupled equation would be a problem here, and the governing equations are non-linear. So again, this is the problem, and determination of pressure is also a problem. So all three statements are complexities encountered in the solution of incompressible flows. So 1, 2 and 3 are problems that we deal with in the solution of the incompressible flows. So we'll see this more clear in the next slide. For example, in the continuity equation, it is given by dou u by dou x plus dou v by dou y is equal to 0. This is for incompressible thing. Generally, how would the continuity equation appear? It would be like dou rho by dou t plus dou rho u by dou x plus dou rho v by dou y is equal to 0. Since in incompressible flows, rho is a constant, so this term becomes 0, and this row we can take it out, and so this term remains. And the momentum conservation equation in the x direction is given by dou u by dou t plus dou u square by dou x plus dou u v by dou y is equal to minus 1 by rho dou p by dou x plus mu by rho dou square u by dou x square plus dou square u by dou y square. It is common over here, and again it is common. So it is okay. So here we can see that here u square appears and uv appears here. So the equation is basically non-linear, and here it is accounting for coupled equations. And again, so these two are again a difficulty encountered here, and here pressure is there, again it should be solved. So solution of pressure is also a problem when we are dealing with incompressible flows. So a coupled equations is a problem, nonlinearity of governing equations is a problem, and determination of pressure is also a problem. And problem in the sense these are difficulties encountered when we are dealing with incompressible flows. We can see that all three are difficulties. So answer to this is 1, 2 and 3. Last option. So this is the right answer. Now we'll move on to the third question. Consider the steady incompressible flow through the contraction section of a circular pipe shown schematically in figure 8.1. For this flow, which of the following can be neglected? Pressure variation in the flow direction, density variation in the flow direction. So the figure was given as, it was like this. Consider a steady flow. So we are dealing with a steady flow. Incompressible flow through the contraction section. So this section we are dealing section of a circular pipe as shown. Of a cylindrical circular pipe. So for this flow, which of the following can be neglected? It is pressure variation in the flow direction and density variation in the flow direction. So from this, since we are dealing with incompressible flows, there would not be any variation in the density. So this can be neglected, whereas pressure variation in the flow direction cannot be neglected. This must be included in the solution of the incompressible flow. Here we already saw that continuity equation, momentum equation in the x direction and momentum equation in the y direction are given. So pressure needs to be solved. So pressure variation cannot be neglected because this term needs to be solved. Whereas since density is remaining constant, here we have neglected the density. So in the similar fashion, we can ignore the density variation in the flow direction, whereas pressure variation in the flow direction cannot be neglected. So the answer to this is wrong, and this is second statement is right. 1 and 2 are wrong. This is also false. So the answer is 2. I hope this is clear. We are ignoring the density variation in the flow direction because we are dealing with the incompressible fluid flow through the contraction section of a circular pipe. Now we'll move on to question 4. If the flow in figure 8.1 is unsteady, axis symmetric and viscous. So we all remember how the figure 1 was. A contraction section was given here and the fluid flow. Here it is given the fluid flow is unsteady and axis symmetric flow. So we can it is like both the across the axis the flow is similar. So we can solve it as axisymmetric flow and viscous fluid flow. How many partial differential equation needs to be solved? It is 5, 4, 3 or 2. So we generally, how many equations do we need to solve? We need to solve one continuity equation and momentum correction equation, balance equation in x direction, y direction and z direction. So the number of equation given over here is 4. But it is given that the problem is axisymmetric. So we can neglect one direction of fluid flow and it would be 4 minus 1. It would be, so therefore 3. We can take only 2 in this and therefore it is 3. Continuity equation plus 2 other momentum balance equations. So when solved or when put together would give us the number of partial differential equation needs to be solved, that is 3 in the current problem. So basically the flow is unsteady flow and the flow is axisymmetric and viscous flow, And how many partial differential equations? So it is continuity equation and two momentum balance equation. It was supposed to be 3, but due to axisymmetry condition we are neglecting -1. Therefore the answer is 3. Now we'll move on to question 5. For the steady axisymmetric incompressible laminar flow case shown in figure 8.1, which of the following statements is true about the stream function vorticity method? So it is given, the figure 8 was like this, 8.1. So in this the flow is steady flow, axisymmetric flow and incompressible fluid flow, and also laminar flow case shown in figure 8.1. Which of the following statements is true about the stream function vorticity method? So stream function vorticity method, what is that? It is a method to solve the incompressible fluid flow. In general, rather than decoupling pressure and velocity and all, this method introduces a new new variables like stream function and vorticity and substitute it in the incompressible flow governing equations and solve those equations so that it would be kind of simpler. This method is mostly used in cases for 2D problems. So based on that, we'll see what are all the statements given below are true. The first one is it cannot be used because the flow is laminar. And second, it cannot be used because the flow is 3D. Third, it cannot be used because the method can be used only for Cartesian coordinate system. So the first statement, we'll see that whether it is correct. It cannot be used because the flow is laminar. No, it is false. Stream function vorticity can be used for the laminar problem also. It can be used for the laminar problem also. And second, it cannot be used because the flow is 3D. In last problem itself, we saw how the problem is axisymmetric. So we can ignore one direction. Therefore, this is also not a problem in this case. And third, it cannot be used because the method can be used only for Cartesian coordinate system. This is also false. Although in this it is a circular pipe, so the coordinates are r, theta and z for the flow direction than the x, y, z. In general, for stream function vorticity method is given for Cartesian coordinates, but it can be used for cylindrical coordinates or any system, because but the equations would be kind of complex in those cases. That is a disadvantage, but it can be used. It is not like it cannot be used, it can be used. So all three statements are wrong. So we'll see which of the following statement is true. The question asked about the statement which is true. So on accounting that factor, we cannot put first statement to be true, and second statement is also not true. Third statement is also not true. So the last one, none of the three is correct, is the right answer. And therefore the answer is none of the three is correct. We already saw how all these three are wrong statements. Therefore none of the three is the correct answer. For 2D incompressible flows, it is possible to recast the Navier-Stokes equation in an alternative form in terms of the stream function and the vorticity. So this is regarding the stream function vorticity approach. As I have already said, this is mostly used in 2D cases. So in 2D cases, incompressible flows, It is possible to recast the Navier-Stokes equation in an alternative form in the form of stream function and the vorticity. So rather than using u, v and p and all, in stream function vorticity approach, what we use is, we use two variables called stream function and the vorticity, and give definition to them. In many applications, stream function or vorticity form of the Navier-Stokes equations provides better insight into the physical mechanism driving the flow than the primitive variables in terms of u, v and p. So basically, in many application, considering application wise, stream function vorticity method is popular because it is giving a better understanding of the problem in terms of stream function and the vorticity variables than the primitive variables in the formulation of u, v and p. So stream function and vorticity formulation is also useful for numerical work since it avoids some problems resulting from the discretization of continuity equation. So basically, for incompressible flow, we have seen the continuity equation is dou u by dou t, dou u by dou x plus dou v by dou y equal to 0. So since some problems would also be arising from the discretization of this one, stream function, because it is having only u and v, not p, variable is not present. Therefore, the problem can also be addressed by using stream function and vorticity approach. So can anyone say what is stream function? Stream function is the like they are used to plot the streamlines of the flow. It is basically used to understand the property of the fluid flow. It is an equation describing the streamline. It is what are streamlines is that in streamlines they are like tangential to the velocity at every point along its length. So there can be no flow along the streamlines. So the function used to represent the streamlines is known as stream function. So this one is used in together with the vorticity to generate equations for solving incompressible fluid flow. Vorticity is it just measures the rotation of the fluid, or basically it is the curl of the velocity. So how it vorticity measures the rotation of the fluid flow. So basically we have two things like stream function and the vorticity. So the stream function, what it gives is that it is a function used to represent the streamlines. So these streamlines are nothing but are tangential to the velocity at every point in the fluid flow. So along the streamlines there would be no fluid flow. That is what streamline gives, and this is given by stream function. Vorticity is the curl of the velocity and it measures the rotation of the fluid flow. So basically this stream function and the vorticity together would be put together in the form of equations, and the continuity equations and the momentum conservation equation would be rewritten to account this stream function and the vorticity and solving these two would be giving the solution of the incompressible fluid flow. So this is a method used in the solution of the stream incompressible fluid flow. So basically in the previous questions it was asked the steady axisymmetric incompressible laminar flow case shown in figure 8.1. Which of this following statement is true? So it cannot be used because the flow is laminar is false. It cannot be used because the flow is 3D is false, because we should see in this context because it is given for axisymmetric flow. In general, it cannot be used for flow in 3D is the true statement. But since it is giving for axisymmetric, we can neglect one. And it cannot be used because the method can be used for Cartesian coordinate system is also false. For Cartesian coordinate system, stream function and vorticity are given easily. For other coordinate systems, it should be given and the solution would become complex. That's it. Now we'll move on to the next question. For the steady axisymmetric incompressible laminar flow case shown in figure 8.1, which of the following statements is true about using artificial compressibility? So in this question it is asked that for the steady axisymmetric, this is figure 8.1. So the flow is given by steady flow and axisymmetric flow, steady axisymmetric incompressible flow, and also laminar flow as shown in figure 8.1. Which of the following statement is true about artificial compressibility method? What is artificial compressibility method? This is a method used to solve the incompressible fluid flow. And this method is similar to the solving compressible fluid flows. Artificial incompressible fluid flow method is similar to solving compressible fluid flow method, wherein we introduce an additional term to compensate for the incompressible thing in the governing equations, so that the dou rho and would not be going into would also be accounted in addition. So artificial incompressibility method is a method used to solve the incompressible fluid flow. In this, we all know, dou rho by plus dou rho this is rho v would be equal to 0. This is the governing equation, and for incompressible fluid flow, this term and this row would be taken out. This would become 0 and these would be taken out. So what if we this equation generally becomes del dot u is equal to 0, right? We'll clear the space. So for incompressible fluid flow in general, it is the case like del dot u is equal to 0. So in artificial incompressibility method, we use one more term, dou rho star by dou t, similar to the compressible equation, and together with this del dot u is equal to 0. So in this case, this rho star is equal to P by beta square. This beta square is known as pseudo compressibility factor. Since this fluid is incompressible, we are using one factor called pseudo compressibility factor and putting it in the governing continuity equation, and then using this equation to solve. So this is known as artificial compressibility method used to solve the solution of the incompressible fluid flow. So basically the flow is given like this. So what the question was asking is which of the following statement is true. So the first statement we'll keep this alone. This is a straight line, not a crosser one. It cannot be used because the flow is laminar. It cannot be used because the flow is 3D. It cannot be used because the flow is steady. So, which of the following statements is true about the artificial compressibility method? So the first one is it cannot be used because the flow is laminar. This one is a false statement. It can be used when the flow is laminar. And second, it cannot be used because flow is 3D. This is also false. And third, it cannot be used because the flow is steady. This is also false. Because we are just extending the compressible equations, governing equations to the incompressible governing equations. So the answer to this problem is none of the three is correct. So now we'll move on to question 7. Which of the following methods can be used for the flow shown in just a moment, guys. We'll just so yeah, we'll resume now. So in previous problems we saw artificial compressibility method. Now in this we are going to see which of the following methods can be used for the flow shown in figure 8.1. So the 8.1 flow was like, the diagram is not so good. Which of the following methods can be used for the flow shown in figure 8.1? McCormack method, pressure equation method, pressure correction approach. So basically we need to understand few things. Here, which of the following can be for the flow shown in figure 8.1? Although this is a flow, we should analyze the given figure first. We will see the first figure. It is given that incompressible fluid flow through a contraction in a pipe of cross section, circular cross section. So basically it is given that it is the flow here is incompressible fluid flow. In a pipe of circular cross section where contraction of the pipe is happening. So basically contraction is happening and the pipe is flow is incompressible fluid flow and pipe is of circular cross section. These are all the details given in figure 8.1. So what are all the methods? When we think of incompressible fluid flow, there are few methods that comes to our mind, like the first one is artificial compressibility method. Next, artificial compressibility method. Next is stream function vorticity approach. Next is pressure correction method, pressure equation method. So these are all the 4 equations. And when we think of compressible fluid flow, what are all the things we should get? One of the approaches we know it is McCormack method. So this McCormack method and implicit beam warming method we saw in last class. McCormack implicit beam warming we saw in last class. For what did we see? Those were used to solve problems governing compressible fluid flow. So in figure 8.1 it is given that the flow is incompressible. So obviously the first one is not correct. Whereas pressure equation method and pressure correction method are completely used to solve for the incompressible fluid flow cases. So the second and third are right answers. So the first option is not true because 1 is present whereas 2 is there, and 2 and 3 is there, so second one is right, and the third one is 1 is given, so it is false, and again 1 is given, it is false. So the answer to this problem is second option, that is 2 and 3. So in the question, in the figure, it is given that it is the flow is an incompressible fluid flow. Therefore, we are using pressure equation approach and pressure correction method. Whereas McCormick method is generally used to solve for the flows governing the compressible fluid flow cases. So I hope this problem is clear. So now we'll see methods for solving incompressible fluid flow. As we discussed in last slide, methods are artificial compressibility method, stream function vorticity approach, pressure equation method, and pressure correction method. These are the available methods for incompressible fluid flow. Incompressible fluid flow. For compressible fluid flow, what are all the methods that we studied? There are various methods, but we in the week 7, the focus was given for compressible fluid flow. McCormick is one and beam warming is the other. Sorry for the poor handwriting. Yeah, so these are for the incompressible fluid flow and these are for the compressible fluid flow. Now we'll move on to the question 8. The pressure correction approach cannot be used for time dependent flows, 3-dimensional flows, viscous flows, none of the above. So we have seen that pressure correction approach is an approach used to solve incompressible fluid flow. So this is one of the popular method, actually, pressure correction approach. The question was about with this method cannot be used for time dependent flows, 3-dimensional flows, viscous flows. So the first one is wrong, it can be used for time dependent flows. Second one also is wrong, it can be used for 3-dimensional flows. And third one again is wrong, it can be used for viscous flows. So the answer to this problem is none of the above. So the answer is none of the above. So what do we do in pressure correction approach? That is what we should see before moving. So in the next slide, we have given the steps involved when we are going with pressure correction approach. So the step 1 is pressure correction method is a class of methods used in computational fluid dynamics for numerically solving the Navier-Stokes equation. Normally for incompressible flows, the steps involved are as follows. First, we would be assuming some initial values for P star, U star and V star, and then we would be solving the discretized x momentum equation for U star and the discretized y momentum equation for the V star. And with these U star and V star would not be solving the continuity equations because these are not true values, they are just guess values. So this value would not be used to solve the continuity equation. Therefore, what we should do is we should find a pressure correction term P star. This would be based on some arbitrary and with some assumptions. This would be calculated, and this P star would be used to correct the pressure back to the original pressure, and similarly this P star would be used to solve the x moment, like used to obtain the velocity corrections U star and V star, and this U star and V star would be used to calculate other scalars like temperature, so on, and this finally pressure velocities would be updated one, and if it is not converged it would be written back to step 1 and the loop would be continued. So answer is this is a pressure correction is a class of methods used in computational fluid dynamics for numerically solving the Navier-Stokes equations, normally for incompressible flows. The steps involved would be, we would be generally guessing pressure P star, U star and V star, and this would be used to we would be having an initial guess values, and from these values the discretized x momentum y momentum equation would be solved for U star and V star, and this would not be solving the continuity equation. Therefore again we should find some correction factors, so we go to solve the pressure correction for P dash values, and this P dash values would be used in solution of used to get the original P values, and similarly U star, U dash and V dash values would be obtained. All these values would be used to solve the other scalars present in the equation, and this would be given to solve the this would be updated P star and U star, and if it is converged it would be the solution, else if not the loop would continue and we would be again solving going from the first step. So this is the steps involved when we are dealing with the pressure correction method. So since it is all the method, so we can say that we can actually solve time dependent flows by using pressure correction method, and three-dimensional flows can be solved, and viscous flows again can be solved. So cannot be used for is asked. So since it can be used for all three, the answer to this problem is none of the above is the right answer. I hope this question is clear. If you have any questions, please feel free to ask by stopping me at any time. Or else you can also take a pen and paper and just see the options given and not see the answer, and just work it out yourself by pausing the video for a minute or so, if in case you are watching by YouTube, or if you are watching the live session, I myself will give a minute break from the for the further questions, so that you people can actually stop and analyze the question and answer it, and then get back to the answer discussion. Most probably all these questions you would have solved, or you would have seen probably when you were solving the assignments, because these questions are taken from the assignment problems of the week 8. So all these questions are also, like in this week questions, the questions are pretty much conceptual and also straightforward. So like understanding wise, it was, the questions were framed in such way, it was checking for our understanding, and it was problematic questions were not there. So yeah, now we'll just move on to question 9. The full form for the simple method is option 1, steady implicit method for pressure linked equations, scheme for incompressible pressure linearized equations, and semi-implicit method for pressure linked equations, steady incompressible method for pressure linked equations. So obviously we all have an idea for what the expansion of the simple method is. It is semi-implicit method for pressure linked equations. So basically this is a numerical approach used to solve for the Navier-Stokes equation. It has been widely used technique, widely used algorithm. This one is an iterative technique, like a pressure correction equation. So this is a form of pressure correction equation, and there are many variants to this simple algorithm that are existing, that are being used, like PSO, CSO, and so on. Simpler, Simplec, everything comes from this, or it is mostly updated with something from this simple algorithm. So yeah, basically simple algorithm, the full form is semi-implicit method for pressure linked equations. So basically we discretize the continuity equation and the Navier-Stokes equation and solve it in a semi-implicit manner. So yeah, we'll move on to question 10 actually. In question 10 it is asked that a staggered grid system is used to enable treatment of flow diameter of the irregular shape, to simplify grid generation, to eliminate checkerboard oscillations in pressure, to overcome the stability problem. So the question asked is staggered grid system. Basically we have like two things, like staggered grid or non-staggered grid systems that are widely used. Why do we prefer, or why do we go for staggered grid system? The options given are to enable treatment of flow domain of irregular shape. No, it is not true. To simplify grid generation. No, this is again not true. To eliminate checkerboard oscillations in pressure. This is true. And to overcome the stability problem. This is again false. So the answer to this question is to eliminate checkerboard oscillations in pressure. So in the lecture itself by the professor, it was clearly explained that we prefer to use staggered grid system to eliminate the checkerboard oscillations in the pressure. So for example, consider a grid where we have the value of pressure as consider we are solving for pressure. Dou P by dou X. I mean we are discretizing for pressure at I comma j. How would we use central difference scheme? It would be with respect to x, so it is pi plus 1 j minus pi minus 1 j divided by 2 delta x. So if we are considering this type of grids like pressure values present in the system, this is known as checkerboard oscillations in pressure. For example, when we are discretizing at this point, consider this is I minus 1, this is I plus 1. So if that is the case, when we are dealing with this pi plus 1j minus pi minus 1j, so what would be we be having? It is 50 minus 50. So it is 50 minus 50 by 2 times of delta x. So this would become 0. So this again becomes 0. So to avoid this type of error in the thing in the solution, we use a staggered grid where the pressure and the velocity are not calculated on the same grid location. For example, this is known as staggered grid, this is non-staggered grid. Consider we have the pressure at this location, calculation at this location. Oh, sorry. Yeah. Can take another color, I guess. This is, yeah, okay. This is P, and cell centered, at cell centered we are having. So if P is evaluated at this point, this is delta x and this is delta y. We would be evaluating it at this point, this point, this point. But in previous cases, what we were doing is we were using the UV at same points. So if U and V are also evaluated at same points, like if it is U and V evaluated at this location, then dou P by dou X would also be evaluated at this location, and it would be becomes 0 as we have seen in the last case. But instead, if we are using the velocity, here we can see that the upward arrow denotes V star. This is present here and here. Right hand arrow denotes U star. This is present here and here. And points denote pressure, temperature, density, everything. So consider we are solving for x momentum equation and discretizing it. So if we know the value of pressure at these points, then it would not be forming checkerboard oscillations. Thereby we can use this location for x velocity calculation and this location for y velocity calculation, and storage of those values, and the cell center would be used to store scalars, that is P. If this is for the case for staggered grid system, if the case is non-staggered grid system, as in the general case study, we can see that the storage location for the V star velocity is where it is yeah, this point. Velocity is given as this direction, and here it is this direction, again here it is this direction, again here it is this direction, and the U star velocity is again given as this direction, and this direction, again this direction. I mean this location, storage location. Here V star is stored at those location and U is stored at this location. And again the scalars like P, T, rho, everything are again stored in this location only. Like storage location is the same for everything. So as we have seen in the previous slide, it is 50-50. We are using central discretized scheme. It would be 50 minus 15. It was becoming 0. So discretizing at the time of discretization, this is giving false results. Like it would be problematic. So we are using staggered grid system where the pressure is evaluated and mostly stored at the cell center, and the velocities, I mean pressure and scalars are stored at cell center. Scalars at cell center, and velocity u, v velocity at grid center, like these points. Where is my pointer? Where is this one, and this one, again this one. So I mean not in this, sorry. It is used in this for storage of velocities or UV. That is what I denoted by grid center. But in general, scalars is denoted at cell center. So thereby the checkered oscillation problem is eliminated to eliminate checkerboard oscillations and pressure. This is question 10. So yeah, these are all the 10 questions that were given for assignments for week 8 problems. Now we'll move on to week 9 problems. So yeah, I mean sorry, not week 9, I'm extremely sorry. It is week 8 problems given for practice. We'll solve those practice problems also. And before that, we'll just take a 5 minutes break and then we'll resume the session. So the time now is 7:07. We'll start by 7:14. Sorry, 7:12. Sorry. So yeah, we'll resume the session now. For three-dimensional incompressible flows, the minimum number of partial differential equations need to be solved is. This is given asked for three-dimensional incompressible flows. We all know we have one continuity equation and one x momentum equation, one y momentum equation, one z momentum equation. So considering all these things, we have continuity equation, x momentum equation, y momentum equation, z momentum equation. So on the whole, we need to solve 4 partial differential equations for three-dimensional incompressible flows. The minimum number of partial differential equations need to be solved is 3, not true. 4 is right, 5 is wrong, 6 is wrong. So the answer to this problem is 4. How are we going to solve those 4 partial differential equations? They are continuity equations, and x momentum, y momentum and z momentum equations. So yeah. So can anyone remember how many partial differential equations we need to solve for three-dimensional compressible flows? One more additional equation we would be solving for compressible equations, that is the energy balance equation. Since the flow is compressible, we need to solve the energy balance or energy conservation equation also, in addition to the all these 3 equations. So there the continuity equation, momentum balance equation and also the energy equation needs to be solved. That is the difference between the compressible flows and the incompressible flows. Now we'll move on to question 12. In question 12, it is asked that which of the following is the characteristic feature of the artificial incompressibility approach to solving incompressible Navier-Stokes equation? So the question is regarding the artificial compressibility approach to solve the Navier-Stokes incompressible Navier-Stokes equation. So what do we recollect regarding the artificial compressibility method used for the incompressible fluid flow? In general, the continuity equation appears as this. Right. So when we are dealing with the incompressible Navier-Stokes equation, this would become 0 since there would be no change in the density, and also this row and this row would go off. So in general we can write it as del dot u is equal to 0. Del dot u is equal to 0. Since there is no density term, we cannot link it with the continuity equation. So in artificial incompressibility method, we use one term like dou rho star plus del dot u is equal to 0. And this rho star is equal to P by beta square. This beta square is nothing but known as pseudo compressibility factor. By using this pseudo compressibility factor, we are converting the incompressible Navier-Stokes equation to be solved in a similar method as the compressibility approach. So this is known as artificial incompressibility approach. The question is regarding this, where which of the following statement is characteristic feature? Pressure need not be evaluated, can be applied to unsteady flows, cannot be applied to three-dimensional flows. The major thing that should be considered when we are dealing with artificial compressibility method is that it can be applied only to steady flows. Only after reaching the steady state flows, the method would get approximate results. So the pressure need not be evaluated is the wrong statement. Sorry, pressure need not be evaluated. This is a correct statement, because in compressible method, if you remember, the pressure equation is solved by using equation of state, not from continuity or the Navier-Stokes equation. So pressure need not be evaluated is the correct statement. Can be applied to unsteady flows is the wrong statement, because only after reaching the steady state, the method would give a proper validation or proper results. And the third statement, cannot be applied to three-dimensional flows, is also wrong. Because it can be applied. It is given cannot, so the statement is false. So obviously the answer is only option 1. Option 1 is right. This is wrong. This is also wrong, since third statement is also given here. This is also wrong. Only option 1 is correct. So answer is option 1. So the thing is, artificial compressibility method is used to solve the incompressible fluid flow. This is an extension of the compressible fluid flow method. So in the continuity equation in the incompressible fluid flow is given by del dot u is equal to 0, where we introduce an additional term like dou rho star by dou t plus del dot u is equal to 0 in the governing equation to make it solvable similar to the compressible flow method. So this rho star is given by P by beta square, where beta square is the pseudo compressibility factor. This factor is introduced to account the incompressible nature of the fluid in terms of this factor. So when we are recollecting the approach used to solve the compressible fluid flow, there we can remember that pressure flow was not solved explicitly. It was solved or obtained from the equation of state. So this first statement is only correct. The major thing with artificial compressibility method is that it can give accurate results only after reaching the steady state. And similarly, it can be applied to the three-dimensional flow also. So the second and third statements are wrong. First statement is the only correct statement. I hope this is clear. Now we'll move to the next question. This is just a note for the question 12. It is given that the main difficulty with the solution of incompressible flow equation is the decoupling of the continuity and the momentum equations due to the absence of the pressure term from the former. We can remember that in the continuity equations, the equation is del dot u is equal to 0. There was no density term in this equation. So pressure velocity decoupling is not possible when we are dealing, pressure is not present in the former equation. So there is a difficulty in using the methods discovered for the compressible flow for the incompressible. So the Poisson equation can be used for calculating the pressure field given a velocity field that satisfy the incompressibility condition both inside the computational domain as well as at the boundaries. So Koren proposed an entirely different approach in order to overcome the difficulty of the pressure decoupling. This approach is called artificial compressibility. This artificial compressibility method was given by Koren. In an artificial compressibility method, a fictitious time derivative of pressure is added to the continuity equation, so that set of equations modified from incompressible Navier-Stokes equation can be solved implicitly by marching in pseudo time. It is limited to steady flows. So this is given that derivative of pressure is added to the continuity equation, so that the set of equations modified from the incompressible Navier-Stokes equation can be solved implicitly by marching in pseudo time. Sorry, this is plus del dot EU is equal to 0. This is the additional term that is introduced in the continuity equation, and it can be used only for the steady flows. So by previous question, the answer is pressure need not be evaluated. It can be obtained in a similar fashion from the compressible solving method. Now we'll move on to question 13. In question 13, it is asked that which of the following variables are evaluated at the same location in staggered grid. So regarding staggered grid, we just saw in the previous, 3-4 problems before. In staggered grid is used to avoid the checkered board pressure oscillation. So pressure are stored at center of the cells, and the u velocity and the v velocity were stored in the phase center or phase center in the cells. So basically, if we are looking at this, we can see that pressure is stored at the center like this, and u velocity is stored in this locations. This is scalar, this is u velocity, and these points are used for storing v velocity values. So from the question, it is asked that which of the following variables are evaluated at same location in a staggered grid. It is u, v, p and t. From this, it is like p and t are scalars. So obviously they would be put in the center of the cell or stored in the center of the cells, whereas u velocity and v velocity would be in the face centered. Or since u velocity is in this direction and v velocity in this direction, they are not stored in the same location. Rather, they are at different phases. Therefore, the answer to this is which of the following variables are evaluated at the same location in a staggered grid. It is P pressure and T temperature, that is scalars. So we'll see the options. It is 1 and 2. 1 and 2 are both at the phase center, but they are not exactly at the same centers. Like they are at different phases. So answer is wrong. 2 and 3, velocity and pressure, one is a scalar, one is a vector, and so they are obviously at different locations. 3 and 4, this is right. P and T both are scalars, therefore they are stored at the cell centers. And option 4, it is 1 and 4. Yeah, it is not 5, it is 4. 1 and 4 are again, one is a scalar and one is a vector. So they are stored at different locations. So the answer to this problem is 3 and 4 is the right answer. That is pressure and temperature. They both are scalars and they are located at the cell center and solved in that fashion. I hope this is clear. Now we will move on to question 14. Which of the following methods requires an equation of state? Stream function vorticity of method, artificial compressibility method, McCormack method. So yeah, first before this we'll just split all the methods into two fashions. The first one is compressible methods for solving compressible fluid flow, and the second one is incompressible fluid flow. Stream function vorticity method is the method in the stream incompressible fluid flow. Stream function vorticity. An artificial compressibility approach is used for solving incompressible fluid flow. And McCormack's method is used in solving compressible fluid flow. And these are the methods given here. And what are all the methods that we know apart from these is beam warming method for the compressible fluid flow. And for incompressible we have two more methods like pressure correction method and pressure equation approach. So these are the methods that we studied in this course. So which of the following methods requires an equation of state? So this equation of state is used to obtain the scalar values like pressure, for example. So in this value is explicitly solved when dealing with incompressible fluid flow methods, whereas in compressible methods this equation of state is required to get the values of pressure or scalars. So the McCormack method given in this is requires an equation of state. And if we look at artificial compressibility approach, we already saw that how this is an extension of the compressible flow method to the incompressible fluid flow solutions. So basically in this method we solve the equation, like in continuity equation it would be generally del dot u is equal to 0. In addition we introduce a term dou rho star by dou t, where this rho star is equal to p by beta square. Beta square we saw it to be an pseudo compressibility factor. So in this artificial compressibility approach, since this is similar to the compressibility flow method, we are in need of equation of state to get the pressure values. So McCormack method requires equation of state, and artificial compressibility method requires equation of state, whereas stream function vorticity method does not require equation of state. In similar way, pressure correction and pressure equation method does not require, and beam warming method again requires. So the answer to this is stream function vorticity method is wrong, and artificial compressibility approach is right, and McCormack method is right. So answer is 2 and 3. 1 is false, 2 is right, 3 is right, and again 2 and 3 is also right. So the answer is 2 and 3. So yeah, that's all. I mean, these are all the problems for today's session. These were taken from the weekly assignment problems of the week 8 along with the practice problems for week 8. So if you have any questions, I'll be very happy to take those questions. So please unmute yourselves and ask the question, or you can type in the chat box. Whichever is convenient, you can do that. Wait for 5 more minutes to solve any queries. If not, we'll just have a quick recap of the session and close the session. The session problems, that's all. Like if there is any doubt, you can feel free to ask, and that would be followed by a quick recap of the session. So yeah, in today's session, we saw about how problems concerning the incompressible fluid flow solution for the Navier-Stokes equation and all the various methods that were involved for that. Like the four major methods that we considered for solution of the incompressible fluid flow are: first one is artificial compressibility method, that is an extension of the compressible solution methods like McCormack method, where we introduce a term dou rho star by dou t in addition to the already existing terms like del dot u is equal to 0. So this term rho star comes from the uh, point where rho star is equal to p by beta square. This beta square is the pseudo compressibility factor. By this we go for the pressure correction, artificial compressibility method. Second is the stream function vorticity approach. In stream function vorticity approach, rather than solving for the Navier-Stokes equation for u, v and p or rho, we go for the solution of we go with the two functions, stream function and the vorticity, thereby modifying the existing Navier-Stokes equation for the continuity, momentum balance, everything, and this is used. Next is the pressure correction method, and in this we initially assume the guess values p star, u star and v star, and then discretize the x momentum equation and the y momentum equation for u star and v star. Obviously this would not be give the correct results because in terms of continuity equation, because these are just assumption values. So again we go for the pressure correction term and modify the pressure and then solve for the u velocity and v velocity corrections, and then put together in that we get the original or true values, and then we repeat this process till we get the converged solution. And one more method is the pressure equation method, where we introduce terms to evaluate the pressure by bringing an equation, additional equation. So thereby we would be evaluating the pressure by knowing the velocity, and then used to solve the continuity equation and the momentum equation, and then we get the pressure velocity and again we calculate pressure. So this would go in a loop until the convergence is achieved. So yeah, this problem was asking about the compressible and the incompressible fluid flows. In compressible fluid flows, in last class itself we saw that we denote the flow to be compressible when the Mach number is less than 0.3 or it is very smaller. What is Mach number is that Mach number is the ratio of the speed of the flow to the speed of the sound in the medium. If the speed of the flow is very small, there is a high chances of the fluid to be compressible. So we denote it as compressible, or we solve such flows using compressible fluid flow method. And this is like what are all the difficulties that we would be encountering when we are going with the incompressible fluid flows solutions. So when we are dealing with incompressible fluid flow solutions, the first approach is coupled equations, and second is non-linearity of governing equations and determination of pressure. Everything plays an important role or plays a major drawback in the solutions. We saw that here non-linearity is present in the momentum balance equations, and also the coupling is present in the momentum balance equation. So non-linearity, coupling, and also the pressure term is present. So determination of pressure, everything plays a major difficulty in the solution of the incompressible fluid flow equations. Next is the this was regarding which one can be this was a question specific, problem specific question which is related to figure 8.1. There a contraction section was observed. Since we are dealing with the incompressible fluid flow, density variation can be neglected in this case, whereas pressure variation cannot be neglected. And in a similar way, the axisymmetric flow case was observed. When we are dealing with axisymmetric flows, one dimension can be cut off, thereby solving in this partial differential equations. Therefore, it becomes three partial differential equations that needs to be solved to get the flow field. And similarly, it was asked for stream function vorticity approach. In stream function vorticity approach, generally it is used for 2D flows, but in this case again it can be used for this three-dimensional problem because it is an axisymmetric problem, and it doesn't mean that it is not possible for Cartesian coordinate system. It is, other than Cartesian coordinate system also, it is can be used, stream function vorticity can be used, but the problem would be that it would be complex equation or a different set of equations that would be arising for the stream function and the vorticity functions. And artificial compressibility method, again it can be used for 3D or steady problems or laminar problems. It can be used, and that it was given that in the figure 8.1 the flow was incompressible. So pressure equation and the pressure correction of the flows that were to be applied. McCormack method cannot be applied in such cases. And the next is the pressure correction approach cannot be used for, no, it can be used for time dependent flows or three-dimensional flows or viscous flows. It is the most popular method. And pressure correction is a simple method. It is like pressure correction method where the expansion is semi-implicit method for pressure linked equations. And staggered grid system also, we have difficulty wherein pressure would be oscillating, so checkerboard oscillations would be coming over there. Like, to eliminate that, we would be using staggered grid. In staggered grid, what we would be doing is that we measure the scalar values at a single point, that would be cell centered, and the vectors like u velocity, v velocity would be measured at the face centered between two grids, but the location of them would be different. So staggered grid system is used to eliminate the checkerboard oscillations. This we saw between staggered grid and the non-staggered grid, where the storage location of the scalars and the vectors are kind of different between these two. And again, minimum number of partial differential equation for three-dimensional incompressible flow is again 4, with 1 continuity and 3 momentum conservation equation. When we were dealing with compressible fluid flows, we were additionally solving for the energy conservation equation to account the compressibility. This is a artificial compressibility method. It is similar to the compressible equation, so pressure need not be evaluated, rather it would be obtained from the equation of state. Other things like can be applied to unsteady flow, cannot be applied to three-dimensional problems. It is not the case. So this characteristic features pressure need not be evaluated. And this is again a staggered grid problem where we saw scalars are in single location and u velocity and v velocity were in different locations. So again, equation of state would be required in the compressible fluid flow approach. So compressible fluid flow is McCormack method, and the artificial compressibility approach is similar to that of the compressible fluid flow solutions. So again, these two are the solutions for this problem. So yeah, these are all the problems that we saw for this. I hope everything is clear, or if so thanks everyone for attending this session. We'll meet again the next week at the same time from 6 to 8. Yeah, thanks everyone. Now we'll close the session. Already it is 7:49. So yeah, we'll close the session. If anyone is having any doubts, please feel free to ask. If not, yeah, it is fine. Thank you guys. Thanks for attending.